Okay, so let us continue with this exercise. We have in fact already started the solution. We have seen parts of it, but since we did not complete it then, so let's go through it once more. We were somewhere in the middle of part B. So in part A, let us once more see what the question is about. R and Q of course are the usual fields, and square root of 2 and square root of 3 are easily seen to be algebraic over the field of rational numbers. We have to exhibit a polynomial of degree 4 in over Q satisfied by square root of 2 plus square root of 3, and such a polynomial is this. Such a polynomial is, what was it, x to the power 4 minus 10x square plus 1. You can easily verify that this is satisfied by this number, and moreover it's a polynomial over the field of rational numbers. In fact, the coefficients are actually integers. Then part B. Okay, so our claim was this. We claim that the degree of square root of 2 plus square root of 3 over over Q is 4. So we already have a 4-degree polynomial over Q which this number satisfies. So it is at most 4, that much we know. Suppose square root of 3 belongs to this extension of Q. Then square root of 3 is equal to a plus b times square root of 2 for some rational numbers a and b. We have already seen before in the previous video why this is the case. That is why root 3 is of this form. If we remember, let's just very briefly go through what we already went through back then. See, this according to the internal realization of this field. This is the smallest field containing both Q and square root of 2. The definition of this field involves taking intersection of all subfields of the field of real numbers containing both Q and root 2, but there was an internal realization where we figured that this is equal to U, where U is the set of all polynomial expressions in square root of 2 divided by, again, polynomial expressions in square root of 2. Where the alpha i's and beta j's are rational numbers n and m are non-negative integers, and the coefficient, the denominator, what is happening to me today, the denominator is non-zero. And then we considered the even and odd powers of square root of 2, and ultimately taking everything into account, we came to the conclusion that square root of 3, the fact that it belongs to this extension implies that it has to be of this form. Okay, so that's where it's coming from. Then we took squares on both sides, so this implies three is equal to a square plus 2b square plus 2ab times square root of 2, since a and b are both non-zero. If a is 0, then b is square root of 3 divided by square root of 2, which is not possible because b is rational and root 3 divided by root 2 is irrational. That can be proved. Just like that, if b is 0, then a is equal to root 3. So root 3 is irrational and a is rational, so that equality is also absurd. So both a and b must be non-zero, and that is why we have root 2 equal to this minus 2b square divided by 2ab. That's why we are able to divide by 2ab. This, however, is not possible, but this is a contradiction. In fact, you can continue the previous line like this. This belongs to the set of rational numbers. The right hand side belongs, this expression is a rational number, so square root of 2 also belongs to it. That is the contradiction. So our supposition is wrong. That is, we must have root 3 not belonging to this extension, and the consequence of this thing is this. Hence, the minimal polynomial of square root of 3 over this extension is x square minus 3. Why is that so? You see, over the field of rational numbers, this is a polynomial that square root of 3 satisfies. So the minimal polynomial, okay, but before that, So because this is a polynomial over q, it's also a polynomial over q root 2 naturally, because q is contained in q root 2. So the minimal polynomial of square root of 3 over q root 2 will have degree less than or equal to 2, but the degree cannot be 1, because the only linear polynomial that is satisfied by square root of 3 is this, which is not a polynomial over this, because this coefficient root 3 or minus root 3 does not belong to q root 2. So the minimal polynomial cannot have degree 1. So the minimum possible degree is 2, and because we are considering monic polynomials, so this is in fact the unique monic polynomial of least possible degree over q root 2 that is satisfied by square root of 3. That is why it's the minimal polynomial of root 3 over q root 2. Okay. So that just means what? It means that the degree of root 3 over q root 2 is equal to 2. So this implies that the degree of this extension over q root 2 which is equal to, need more space, this is equal to 2. Okay. Since we already know that the degree of q root 2 over q is 2, so theorem 511 implies that this degree, which is equal to the product of this degree and this degree, is equal to 2 times 2, 4. This is 4. Okay. Also, since this extension q root 2 comma root 3 contains this extension, which in turn contains q. So the corollary to the first result, to theorem 511. Implies that the degree of this intermediate extension over Q divides the degree of this over Q, that is, it divides 4. Implies I think it will be better to mention what that 4 is. Which is equal to 4. Okay. In this line, how are we getting the first inclusion? See, this extension, besides having Q as a subset, it also has the elements root 2 and root 3. So this extension is a subfield of the field of real numbers that contains, because it contains root 2 and root 3, so it also contains root 2 plus root 3, and also definitely it contains Q as a subset. So this becomes a subfield of R that contains both Q and root 2 plus root 3, and this is the smallest subfield of R containing both Q and root 2 plus root 3. So that's how we are getting the first inclusion. Okay, so the inclusions are clear, and the second one of course is clear. And now this means what? It means that as a vector space, Q root 2 plus root 3 is a subspace of Q root 2 comma root 3 over Q. And so by the corollary to theorem 511, its dimension over Q, which is this degree, will divide the dimension of the larger one over Q, which is that degree, and this is 4. So the possible values of this are 1, 2 and 4. It will be a positive divisor of 4. Hence, or 4. Okay. Now we can rule out one immediately, since root 2 plus root 3 is an irrational number, which one can prove quite easily by elementary number theoretic methods. Since this does not belong to Q, this degree is not equal to 1. Okay, so it cannot be 1. So to prove that, to prove our claim, that is the degree is actually 4, we now have to rule out the case 2. So its degree cannot be equal to 2. That's what we want to show. So let us start by supposing. Suppose to the contrary, that the degree is actually equal to 2. Okay. Now in another paragraph we do a little something. This is where I think we ended the previous video. Now we prove that for any field f and any extension E of f the minimal polynomial of some element a in E over f divides any polynomial over f that is satisfied by a. Let me refill. Satisfied by a. So let us denote the polynomials by some symbol. Let px in fx be the minimal polynomial of a. Now, since we are writing over f, there was actually no need to write this, that px belongs to fx. Over f means it's in fx. And let fx be a polynomial that the element a satisfies. Okay. Now the minimal polynomial by definition is a monic polynomial. It is a non-zero polynomial because of that. So in the polynomial ring fx, we can divide fx by px using the Euclidean algorithm. Since px is a non-zero polynomial, there exists polynomials qx and rx in fx such that fx is equal to qx times px plus rx. Where either Rx is the zero polynomial or Rx is a non-zero polynomial and its degree is less than the degree of the divisor, that is degree of Px. Okay, now we invoke the fact that Fx is satisfied by A and Px is also satisfied by A, because after all Px is the minimal polynomial of A, means it's a polynomial that A satisfies, and additionally it has the smallest possible degree, and because of the way we are choosing minimal polynomials, it's monic also. Now since f of A is 0 and P of A is also 0, so we have 0 equal to Fa, this is equal to Qa times Pa plus Ra. Now because this is 0, this term will be 0, so this is equal to Ra. So that means the polynomial Rx is also satisfied by A. Now if we suppose, or in fact let's just write the argument directly, since Px has the least possible degree among the polynomials in fx, that are satisfied by A, we cannot have this condition, because if Rx is non-zero, then it's a polynomial which is satisfied by A and its degree is less than the degree of Px, so that contradicts the minimality of the degree of Px. We cannot have and degree of Rx less than degree of, actually this condition that Rx is non-zero is a part of this, because if Rx is 0, then degree of Rx has not been defined, it's undefined in this book. So this automatically also means in particular that Rx is non-zero. We have written it alongside this inequality just to emphasize the fact that we want to use it. We want to stress that Rx cannot be non-zero. Thus Rx is equal to 0. But if Rx is 0, then in Fx, Px divides Fx, and that's what we wanted to prove. Okay, but this implies Px divides Fx in Fx. Okay. Okay, now we come back to our problem. Now, because of this result, this small result we proved, we can, the solution now progresses like this. Since root 2 plus root 3 satisfies that polynomial that we wrote in part A, x to the power 4 minus 10x squared plus 1. So the minimal polynomial of root 2 plus root 3 over q divides this polynomial. And now it's time for factorization. Now one can routinely verify that the given polynomial given means this one, it can be factorized like this. Times x plus root 3 plus root 2 times, won't be able to write all the factors in one line, times x plus root 3 minus root 2. To see that this is true, you just have to perform the multiplication on the right hand side and you will get this one. Okay, so that means what? The minimal polynomial of root 2 plus root 3 over q has to divide this. Okay, now since the minimal polynomial at the same time should also be satisfied by root 2 plus root 3, so this factor must be there in the minimal polynomial. Note that none of the other factors is satisfied by root 2 plus root 3. So there are 3 possibilities for the minimal polynomial. So the minimal polynomial of root 2 plus root 3 over q is either you multiply this one with this one, or this one with this one, or this one with this one. Or x minus root 2 minus root 3 times x minus root 3 plus root 2, or x minus root 2 minus root 3 times that other one, x plus root 3 minus root 2. Keep in mind that according to our supposition, what was our supposition? We supposed that the degree of root 2 plus root 3 over q is actually equal to 2. So that means the minimal polynomial should be a quadratic polynomial. That's why we cannot just simply consider this one, which anyway is not possible, because we have already seen that root 2 plus root 3 is not in q. So this cannot be the minimal polynomial of root 2 plus root 3. So that degree being 1, that case has already been ruled out. But there is a problem here, and we want a problem because we are hoping for a contradiction. The thing is that none of these three polynomials is actually over q. If you perform the multiplications, you will see that not all the coefficients are rational numbers, but none of these three polynomials is in qx. This is a contradiction, and proves that the supposition that this degree is 2 is wrong. So the only choice left is that the degree must be equal to 4, and that was our initial claim. So the claim has now been proved. So this is part B, and part C is not that difficult. Note that, so in this case we have to find the degree of root 2 into root 3, that is root 6 over q. So this satisfies this quadratic polynomial in qx. So the degree of root 2 plus root 3 is at most 2. So now you have to decide whether it's 2 or 1. But for the degree to be 1, the element itself should belong to the field of rational numbers, which is not true, since root 2 root 3 does not belong to Q, the minimal polynomial cannot be this. Polynomial of this over Q, that is understood from the context, it cannot be this. So the degree is 2, it cannot be 1. So root 2 times root 3 has lower degree, it has degree 2, but root 2 plus root 3 has higher degree 4. So the solution ends here. Next, 5. Exercise 5 with same notation as in exercise 4. Same notation as in exercise 4. Show that square root of 2 plus cube root of 5, okay, is algebraic over Q of degree 6. So here also we had to wrestle with many things. Okay, so let us see the solution. Because of the presence of square root and also cube root, the degree has become 6. So for the sake of notational simplicity, we denote it by some symbol. Let the number in question be denoted by alpha plus cube root of 5. Then okay, so what is it we have done? Oh, we have taken cubes on both sides, and after a little bit of calculation we end up with a thing like this: alpha square plus 6 alpha minus 2 root 5 equal to five. Oh, this I believe is obtained by first subtracting root 2 from both sides, so that we have alpha minus root 2 equal to cube root of 5, and then taking cube root, cubes on both sides. So that will give us this. But one thing is a little okay. Is it really true? How are we getting root 5 here? Let me just quickly see if the calculation is correct. Okay, so this will be alpha cube minus 3 root 2 alpha square. This will be minus will become plus, square root of 2, this will be 2, so plus 6 alpha minus will stay minus because cube 2 root. Okay, see, there is a mistake. It will not be 5, it will be 2. So that's what I was thinking. Okay, anyway, I hope this is not a fatal mistake. Unlikely, this is just one value. Okay, so we have got this. Now this can be written, so now I have to be more careful because I have spotted a mistake. Or, so what is the next thing? The next thing is take the irrational numbers, or I should not say irrational numbers, but the terms involving root 2 on one side. Okay, so alpha cube plus 6 alpha minus 5 is equal to, so if we take all the things on that side and also take square root of 2 common out, then we have 3 alpha square plus 2. Also in the next line it's written correctly, so that is just simply a small error. Okay, now squaring both sides, we get the next expression. I hope is correct, but you have to verify all these things. Okay, for me it's a request. Alpha to the power 6, so we will ultimately end up with a thing like this: minus 6 alpha to the power 4 plus 10 alpha cube plus 12 alpha square minus 60 alpha plus 8 equal to 0. Okay, so you square both sides and you get an expression like this. That is alpha satisfies a monic polynomial. Note that the polynomial is monic. Of degree 6 over q. So we know that the minimal polynomial will be of degree at most 6. We have to prove that it is actually equal to 6, and because this is a polynomial that is satisfied by alpha, which is of degree 6, and it is also monic, so once we prove that the degree is 6, this will be the minimal polynomial because it is unique. Okay, so what is the next thing? So the degree of alpha over q is at most 6. From the above calculations, we also get something else. we also get this thing. Square root of 2 from here is equal to alpha cube plus 6 alpha minus 5 divided by 3 alpha square plus 2. Note that 3 alpha square plus 2 is positive, it can never be negative. And this thing, you see, it's a quotient of two polynomial expressions in alpha, and that is why it belongs to this extension of Q. Extension of Q obtained by adjoining alpha to Q. And if we want, we can also write this. Note that although this is understood, but still this is not equal to 0. So what is the implication? This implies that cube root of 5, which is alpha minus square root of 2, this also belongs to that extension Q alpha, because now we have proved that root 2 belongs to this field and alpha already belongs to the field, so their difference also belongs to the field, which is nothing but cube root of 5. Okay, so root 2 and cube root of 5 both belong to this extension. So what does that imply? It implies that this extension is contained in this, and this extension is also contained in this. Why? Because you see, this extension, of course, it contains the field of rational numbers Q as a subfield, but at the same time it also contains root 2. So it will contain the smallest subfield containing both Q and root 2. Similarly, since it contains this as an element, so it will contain the smallest subfield containing Q and cube root of 5. So that's how we are getting these two things. So again, now we can apply the corollary to theorem 511. So by the corollary to theorem 511, so what is the corollary now saying? It is saying that these are subfields of this Q alpha. So the degree of this one over Q will divide the degree of this over Q, because it is a subspace. This degree. Divides this degree, and this degree we already know is 2. Just like that, 3, which is the degree of this extension over Q, also divides this degree. Now 2 and 3 both divide this, it's a positive integer after all. Because 2 and 3 are relatively prime, so their product will also divide this. Thus 6 divides this degree, which implies but we have already seen that this degree is at least at most 6. Here we have shown that it's at least 6, so that means it must be equal to 6, since we already have the conclusion is this. I don't think the 6-degree polynomial that we have found, even if there is a mistake, that actually kills the solution. Because you see, we have not really used the fact that the polynomial has this and this coefficients. We just used the fact that there is a 6-degree polynomial which the given alpha satisfies, and also we are dependent on this fact. However, that does not mean that you can keep a mistake and claim that it's a solution. If something is wrong, then the entire solution is technically wrong. So you please go through that squaring part, okay, square on both sides and see that the 6-degree polynomial we have obtained is actually the thing. Okay, so with this the solution is over. Next, so this was exercise 5. Next, exercise 6, and this is a start one, so it is supposed to be a little more difficult than the usual. Find an element u, find a real number u such that also it's related to the previous exercise, that this extension actually is equal to this extension obtained by just adjoining u to q. So that can be achieved by adjoining some single real number to q. And then in part B, in this extension, characterize all the elements. All the elements W such that if one considers this extension, if one adjoins W to Q, then that is not equal to the original extension. So we have to find all the elements W which are not like U. So let's see the solution. So in part A, we want to find a U. So we start like this. We know from the previous exercise means actually its solution. You can understand that both root 2 and cube root of 5 belong to Q alpha, where alpha is their sum, root 2 plus cube root of 5. So because we are writing from the previous exercise, so we are not mentioning what alpha is. We already know it is root 2 plus cube root of 3. Now the previous exercise also shows that the degree of this extension Q alpha over Q is equal to 6, and okay, so at this point we have to take the help of exercise 8, which we haven't seen yet. But I was not able to solve this problem without using exercise 8. If you can come up with a solution that does not use exercise 8, then please let me know. And by exercise 8 below, what do we have? We did not. Okay. Yeah, this one we did not find. 8 below, the degree of this extension obtained by first adjoining root 2 to Q and then adjoining cube root of 5 to that extension over Q is equal to 6. Okay, this degree is equal to 6. And this you can see that in exercise 8 we are going to prove this. So which is again some solution like these things that we have been seeing here. So it's nothing really very difficult or unfamiliar. Hence, okay, so now you look at this. You look at these inclusions. We already know how the second inclusion is coming. We have already seen one such where we had only square roots, root 2 plus root 3. Like that this one is coming, and the reason simply is that this extension has the elements root 2 and cube root of 5, so it also has their sum, and so this is a subfield containing both Q and root 2 plus cube root of 5. So it will contain the smallest subfield containing q and root 2 plus cube root of 5. So that means this is a vector space over q, this is a subspace over q, and they have the same dimension, which is 6. So they must be equal. A proper subspace of a vector space always has a strictly smaller dimension, provided we are talking about finite dimensional vector spaces. Hence, this is equal to q alpha. Okay, so this is the conclusion. And that's it. That is the first one. No? We had to find a u, so that alpha from the previous exercise is one such u. Then in part B, this one will be a little longer. We have to characterize those real numbers w, of course, in this extension itself, for which this extension is not equal to the original one. That means this is going to be a proper subspace of this. So let us consider any w here. Okay, such that also first we consider one w for which this inequality is true. Since this is contained in this, the corollary to theorem 5.1, it's these things we don't have to write again and again, provided if Herstein cared to give a number to this corollary, we could have directly referred to that number. Implies that the degree of QW over Q divides this degree, which is 6. Okay, so the possible degrees are 1, 2, 3 and 6. Since this equal to 6 implies that Q of W is equal to this, which is not true, of course, because we assume W to be a number for which we don't have equality, but this degree implies that we must have equality. So that means this cannot be 6, it will either be 1, 2 or 3. we must have one or two or three. Clearly, the set of elements in of degree 1 over Q is Q, which is almost obvious, but I leave to you to figure out that this is the case. Only the elements in the underlying field have degree 1 over the field, and this is always the case. If you have an element outside, then it can never be of degree 1 because it cannot satisfy a linear polynomial. For it to satisfy a linear polynomial over, say, Q, the element must itself be inside Q. So all the 1 degree elements are the rational numbers. Next, we claim that the set of all elements in Q root 2 comma cube root of 5 of degree 2 over Q is Q root 2 minus Q. Okay, that is our claim. So let X be an element in Q root 2 minus Q. Okay, and but we did not use that fact. Fine, whatever gets the job done is okay. Since this is contained in Q root 2, so its degree must either be 1 or 2. The corollary to theorem 511 implies that the degree of Qx over Q divides the degree of Q root 2 over Q, which is 2, and so this is either 1 or 2, but the degree cannot be 1, because if the degree is 1, then X will satisfy a linear polynomial over Q, which will force X to be inside Q, and that will contradict our choice of x as an element that is not in Q. Okay, since x does not belong to Q, we cannot have this is equal to 1. Thus, this is equal to 2. That is, this apparatus is amazing, no? We can jump from polynomials to extensions and their dimensions over the underlying field. We can then use number theory and divisibility to guess the dimension, and then again we can come back to polynomials. This is really amazing. That is, x is of degree 2 over Q. So that is one half of our claim. We have shown that any element in this set has degree 2 over Q. Next, we have to prove that these are the only such elements. We don't have any other elements outside of this set that also has degree 2 over Q. For that, we proceed like this. Next, suppose y belongs to has degree 2 over Q. So that means we are now outside of this. Then y has degree at most 2 over Q root 2. Y having degree 2 over Q means the minimal polynomial of y over Q is of degree 2. Now that minimal polynomial is also a polynomial over Q root 2. So the minimal polynomial of y over Q root 2 will either be that polynomial or a polynomial of lower degree. So that's why we are writing then y has degree at most 2 over Q root 2. Okay. Since y cannot have degree 1 over Q, what is the reason? As y does not belong to Q root 2 and Q root 2 contains Q. Q root 2 contains Q, so that means since y is not there in q root 2, so it cannot be a rational number, and we have already noted that the only elements of degree 1 over q are the rational numbers. So y cannot have degree 1 over q. So the degree of y over q root 2 is exactly equal to 2. That is our conclusion. But then what goes wrong? Okay, so by theorem 511, the degree of q root 2 comma y, okay, over what? Over q root 2. This is equal to and that is equal to 2. Now what is the degree of this thing over q this is equal to, excuse me, this is equal to this degree. In fact, let's just write that because we are going to use it now. Times the degree of q root 2 over q. This one we have found to be equal to 2, and this we already know is 2. So 2 times 2, this is equal to 4. Again by theorem. Oh, then why did we write by theorem 511 here? This is not theorem 511, no? The degree of y over q root 2 being 2 and this is not theorem 511. I think it is either theorem 512 or theorem 513, I think. You please verify, okay? You understand what we are doing here. You just put the correct number here. Anyway, so by theorem, this one is of course an application of theorem 511. So this degree is 4. So by the corollary to theorem 511, 4 must divide. Yeah, now we have got a contradiction. This must divide 6. A contradiction. Okay, let me just see one thing. We have chosen y from here after all, the original, the largest extension in this discussion. So that means this extension contains of course q as a subset and it contains y. So it contains this extension as a subfield. So yes, its degree over q will divide this field. Okay, fine. So that is a contradiction. This implies that our last supposition is wrong. That is, no element of this set can be of degree 2 over q. So the set of all elements in this extension that are of degree 2 over q is the set that we were claiming to be the set. So this part is over. Okay, next, degree 3. That, however, we will not go through the details. We will just simply write similarly. However, I urge you to what we usually do. I urge you to verify the similar part. Similarly, one can show that the set of all elements in this extension that are of degree 3 over q is that other thing, that is this extension obtained by adjoining cube root of 5 to q minus q. So what is our ultimate conclusion? We assumed w to be an element in this extension for which this is not equal to this. We wanted to know what W is. We then found out that the degree of W over Q should either be 1 or 2 or 3. It cannot be 6, and these are the only possibilities. So then it means we had to find all the elements of degree 1 and 2 and 3 over Q. The set of all elements of degree 1 is this. The set of all elements of degree 2 is this, and the set of all elements of degree 3 is this. Anything else you take, its degree over Q must be equal to 6. So that means the set of those W for which we have this inequality is the union of these three sets, which is the union of this and this, because Q is contained in both of these sets. Hence, we can write our conclusion like this. The set of all W here such that QW is not equal to this extension is this extension union this, or in fact let us just show how we are getting this thing. This union this which becomes so that is the characterization of all such W. So here the solution ends. After this we have some exercises that address. The seventh one addresses this question. Remember, we mentioned this fact while going through the results in this section, that one can show that we can change the order. Changing the order of these elements actually changes the meanings of these things entirely. This is by definition, this is the smallest subfield of whatever extension we have of F. Smallest, say that extension is K. This is and A and B are suppose elements in K. By definition, this is the smallest subfield of K containing both FA and B. On the other hand, by definition, just like that, this is the smallest subfield of K containing both F, B and A, and it's not immediate that they should be equal. We have to prove it. So that we will see in exercise 7 and its general version, where we have any number of elements and you can permute these elements. You can take any permutation of the indices, and you can, loosely speaking, you can change the order of these elements in whatever way you want. Still you will end up with the same extension. So this we will see, and then there are some other things also. So we will continue in the next video. Ideally I should have solved at least one or two more exercises, but I'm not feeling like it today because of that incident. So anyway, see you in the next video. And oh, one more thing I forgot. The vector space video you will get in the next week on Monday. So we will alternate between vector spaces and modules and field theory. So with that, this is me, Lucifer, from a mathematical room. Have a nice night.